Welcome to lecture 2.4, where I'm going to teach you how to quickly identify hybridization in a molecule using a simple trick and the idea of an electron group. In previous lectures, 2.1 through 2.3, we went into the fundamentals of hybridization and some consequences of them, why they're important. However, when it comes to the core fundamental skill of hybridization, the most important thing you'll need to be able to do in organic chemistry as a whole is be able to look at a molecule and quickly ascertain what its hybridization is and what that means, what the shape of that molecule is and its bond angles, for example. Drawing out the orbital diagrams is simply not going to be a good way to do it, but I'll show you a very fast way to approach this kind of problem. Now, to do this, let's quickly revisit the octet rule and introduce an alternative way of looking at these bonds. So the octet rule states that you're going to need 8 total electrons around any atom, so surrounding it, whether that be in bonds or lone pairs. So in the case of the carbons we've been looking at, a single bond is going to be worth 2 electrons, as it's composed of 2 electrons. And the double bond, similarly, will be viewed as 4 electrons, as it's composed of 4 electrons. The triple bond will be viewed as 6 electrons, and a lone pair will also be viewed as 2. You'll see that in the next sections to come with formal charge, we're going to actually change this around a bit. But for now, this is how we view the octet rule. And it is important that our atoms obey the octet rule. Now, the alternative definition I want to give you is this concept of electron groups. I like to call this the definition of things. It's really just that simple. We're going to kind of count how many things each one of these represents around an atom. So say we have a bond, that's one thing around our atom. A double bond, you might be tempted to say that it's 2 things, but it's really just one thing around an atom. If I look at this carbon has 3 things around it. It just so happens to be that one of those things is a double bond. So that's one thing as well. And at this point, you can probably see where this is going. Each of these things is just one thing. Seems kind of silly to say. Let's just quickly practice spotting electron groups before we move forward. So first, let's look at this aromatic benzene ring, and specifically the carbon I've circled in red. So considering the octet rule, we have a bond to hydrogen, a single bond to carbon, and a double bond to another carbon, making a total of 4 bonds. 3 single bonds and 1 pi bond, or 3 sigma bonds, 1 pi bond. In total, that's going to be 8 electrons, and our octet is satisfied. However, looking at the number of electron groups, I only count 3. The hydrogen, or more specifically the hydrogen bond, the single bond to the carbon, and the double bond, giving us 3 electron groups. On to the next, here's an oxygen, and we can see that the same rules can be applied to the heteroatoms such as oxygen and nitrogen. The octet rule here is satisfied, as we can see that there's 2 lone pairs making up 4 electrons, and 2 single bonds making up the remaining 4. So the octet rule is satisfied, but in terms of the number of groups around, we can see that there's actually now 4 distinct electron groups, 4 things around that atom, giving us an electron group of 4. And for the last example, let's look at this nitrogen. It's connected via a triple bond to carbon and has 1 lone pair. Now, its octet, we can see it has 2 electrons from the lone pair and 6 electrons from the triple bond, as per what we discussed up there. So 8 electrons once again. All of these arrangements of atoms satisfy the octet rule. Now, if we look at the number of electron groups, however, we're only going to count 2, the lone pair and the triple bond. Again, the triple bond is composed of all these electrons, but we're going to view it as one thing in this definition. So we have 2 electron groups. Great, so that'll be a useful tool, simply counting. The highest you'll have to count to is 4 for example, as we did here. Now, how are we going to relate this to our hybridization? Well, very easily, actually. If you have 4 electron groups, like in the case of water here, that means that you're going to have 4 letters in your hybridization. That's the trick. So the only way to have 4 letters in your hybridization is to use the sp3 hybrid. So if your atom has 4 electron groups around it, as we've defined up here, 4 things, that means that your hybridization is going to be sp3. And from that quick, counting to 4, you'll also be able to ascertain that the shape is tetrahedral. Now, the way we typically draw tetrahedral structures, and we will revisit this, is 2 straight lines to the atom, 1 wedge, and 1 dash. There are other ways to represent this, but this is the most common, representing 4 distinct things. Now, VSEPR, or valence shell electron pair repulsion theory, tells us how these structures are made. This can be quite overcomplicated. I would say that essentially you have 4 different things that are repelling each other. These electrons don't want to be near each other. And so the best way, imagine if you have a little ball here, to put these 4 substituents on this ball, if they're all repelling each other, the best structure is going to be the one where their distance is maximally apart. And it just so happens to be that that's going to be a bond angle of 109.5 and a tetrahedral shape when you've got 4 things on that ball. When you have 3 electron groups that you count, so for example, in the case of this oxygen with 2 lone pairs and 1 double bond, then your hybridization has to have 3 letters. And that's going to leave you with SPP, or the sp2 hybrid. Now, that is going to lock you into the trigonal planar shape, as we discussed earlier. And this one is a lot easier to draw. It's simply a triangle with 3 connected things, as far apart as they can in a flat plane. That's what planar means. And the bond angle here is going to be 120 degrees. Again, VSEPR is how we understand this shape, but you're only going to have to deal with 3 of these shapes in organic chemistry, which is very handy. Now, 2 electron groups, as our last situation, is going to leave us with 2 letters, or the sp hybrid. In this case, we're always going to have a linear structure. One common mistake many students make, in my experience as a TA and tutor, is drawing things like this, right? When we draw single bonds, that's acceptable. When we draw double bonds, that's acceptable. But with the triple bond, that's not going to work. Whenever a triple bond is used, both carbons have to have a linear arrangement of atoms. And so that's going to look something like this, whatever is connected to either side, because we want those 2 things to be as far apart as possible, right? They're repelling each other with a 180-degree bond angle. Awesome. So now we've learned that by counting the number of electron groups, you're able to quickly ascertain the hybridization without going into all that orbital diagram stuff that we did previously. Let's do some quick practice just to wrap up this skill and solidify it. Here we have a much more complicated molecule with 4 atoms singled out. Feel free to pause the video now and take a stab at identifying the hybridization and the bond angle of each of these atoms. The carbon here, the oxygen here, the nitrogen here, and the nitrogen there. If you paused, now let's go through. Otherwise, we'll go through and figure out what the hybridization and bond angle is. So for atom A, we have a carbon, and we can see that that carbon is connected to 3 distinct groups: a hydrogen, a double bond, and a single bond. So if we have 3 groups, that's going to tell us that the hybrid is sp2 and that the bond angle is 120 degrees, that this is a trigonal planar structure. And just a fun fact, whenever you see a benzene ring like this, every single atom in that ring is similarly going to be sp2 hybridized, making the whole ring flat like a frisbee. Now let's jump to B. We have an oxygen here. We can see that there are 3 different electron groups: a lone pair here, a lone pair here, and the double bond. And so you can see that, yeah, we did the carbon example, we didn't do the oxygen example, but the same rules apply just as well to oxygen. If we have 3 electron groups, then we're going to have an sp2 hybrid. And it, as the same, is going to have a 120-degree angle. Now, to be clear, when we have lone pairs, we don't really worry about this angle as much. It's more relevant when there's a bond, but it's still something good to memorize in regards to hybridization. Now, let's look at C. Now, C is a nitrogen. Well, we haven't done nitrogen yet, but once again, the same rules apply. We can count the number of groups around that nitrogen. We can see that there's a hydrogen, which I did not draw this in, but there is a bond connecting it. We have this bond, we have this bond, and we have this lone pair, making up a total of 4 distinct things. So 4 things means 4 letters. We need the sp3 hybrid, which means the shape of this is tetrahedral, and there's going to be some 3D structure around that nitrogen. The bond angle, of course, being 109.5 degrees. And for the last example, we have another nitrogen, this time in a triple bond. Now, we've seen triple bonds before with the alkynes, but nitrogens can be triple bonded as well. We can see here that there's 2 electron groups, a lone pair, and a triple bond, making up 2 electron groups, which informs us that this is the sp hybrid of nitrogen, and that the bond angle must be 180 degrees. Hopefully this helps with quickly identifying your hybridization. And now that we've tackled hybridization, it's time to move on to formal charge to really wrap up the fundamental skills that underline the drawing of chemicals in OChem. So I'll see you there.